Okay, so what does it even mean for a problem to be really difficult? Not just, annoying, but fundamentally hard to solve. And how do the beautiful structures of logic, the systems we use to reason, how do they run up against these computational brick walls?
Yeah, it's a fascinating question, isn't it? The idea that there might be limits to what we can compute, even with unlimited time and resources.
Right. Welcome to the deep dive. We take your sources and we try to extract the pure knowledge you need efficiently and hopefully with a little bit of intellectual sparkle. Today we're going deep into computational complexity theory. We're using the Stanford Encyclopedia of Philosophy, a super reliable source, and this is a field that really grapples with the inherent difficulty of computational problems.
And it's a topic that's, I think, especially relevant for those of you who enjoy, getting right to the heart of complex ideas. This deep dive is going to give you a new framework for understanding the boundaries of what we can actually compute, what's actually possible with algorithms.
Exactly. So it's you have this source, the Stanford Encyclopedia of Philosophy. It's a great source, by the way. You can trust what it says. And today we're zeroing in on how computational complexity theory directly connects with logic and philosophy itself.
Absolutely. I mean, this isn't just about computers crunching numbers. It's about the limits of knowledge, what we can know, and how we can know it.
Exactly. We want to think of this deep dive as your cheat sheet to grasping a field that goes way beyond just computers, way beyond just silicon and circuits. It touches upon the very limits of knowledge, of what we can achieve through algorithmic reasoning. Are there some things we just can't figure out no matter how smart we are or how powerful our computers get?
Big questions, yeah.
Big questions, right? Okay, so our mission here is to, shine a light on the core concepts of computational complexity and then, and this is the fun part, explore how it intersects with philosophical questions, especially those about decidability, feasibility, and the limits of knowledge. Okay, so let's break this down a bit. For a philosopher who's thinking about, the deep nature of problems, what exactly is computational complexity getting at?
At its core, computational complexity theory is all about how hard it is to solve certain problems, but specifically on a large scale. It frames these problems as decision problems, meaning the answer is either yes or no. And the Stanford Encyclopedia gives some great examples like the off-pro primes, which is just the set of all prime numbers. And
yeah. Okay, so that's if you're a philosopher thinking about the essence of primality, the problem is figuring out if any given number is prime or not.
Yeah.
And then Thornting, that's more if you're thinking about relationships or assignments, can you perfectly pair up things in a network without any overlaps?
Exactly. And, from the perspective of computability theory, which philosophers have been thinking about for a long time, these problems are generally considered decidable in principle. That means we know there are algorithms out there, step-by-step instructions, that can eventually give us a yes or no answer for any input.
Okay, so theoretically we could solve them.
Right. But computational complexity goes a step further. It's not just about whether a solution exists, but how efficiently we can find that solution, especially when dealing with, huge amounts of data.
So it's not just can you find a perfect matching, but can you do it quickly, even when you have a massive complicated network? And that's a question that matters in the real world, right?
Yeah.
Think about, optimizing resource allocation or understanding how social networks work.
Precisely. And efficiency here is usually measured by how much time and memory an algorithm needs.
Mm.
So you have time, which is the number of steps a computer takes, and then you have space, which is how much memory it needs to store the information.
Right. Makes sense.
So computational complexity theory gives us a way to analyze how these resources, time and space, scale as the size of the problem grows. And for a philosopher, this is where it gets interesting. It helps us distinguish between problems that have efficient solutions and problems that are just inherently hard, maybe even impossible to solve efficiently, even though we know, in theory, a solution exists.
So, it draws a line between what's theoretically possible and what's actually doable in practice.
Okay, I'm starting to see how this connects to philosophical questions about, the limits of reason and knowledge. Can we look at some concrete examples that really drive this point home?
Absolutely. Let's go back to the problem of determining whether a number is prime. Philosophers have been obsessed with prime numbers forever, right?
Right, the building blocks of numbers.
Exactly. And for centuries, figuring out if a number was prime was a challenge. But in 2004, they discovered something called the AKS primality test. This test is special because it's a polynomial time algorithm.
Okay, polynomial time. That sounds a little technical. What does that mean in plain English?
Basically, it means the time it takes to determine if a number is prime using this test grows at a rate that's described by a polynomial function of the number of digits in the input.
Okay, so as the numbers get bigger, the time it takes to solve the problem doesn't explode exponentially. It's more manageable. Exactly. It's considered feasibly decidable even for massive numbers.
Okay, so went from a hard problem to a relatively easy problem.
That's right.
What about some related problems like relative primality, which is like checking if two numbers share any common factors besides one, and then scratcherization, which is breaking a number down into its prime factors.
Those are perfect examples to illustrate the difference between easy and hard problems. So there's relative primality. That goes way back. The ancient Greeks had an algorithm for that called Euclid's algorithm, and it's remarkably efficient. The number of steps it takes is proportional to the logarithm of the input numbers.
Logarithm. Okay, another technical term. Can you unpack that a bit for us non-mathematicians?
Sure. Think of it this way. Even for ridiculously huge numbers, Euclid's algorithm finds the answer incredibly quickly. It's so efficient because the number of steps is related to the number of digits in the input, not the actual value of the number itself. So even if the number itself is astronomically large, if the number of digits is manageable, the algorithm remains fast.
Okay, so the process itself doesn't get bogged down, even if the numbers are enormous.
Exactly. Now contrast that with factorization. That's one that feels intuitively harder, right? It's like, you have this big number and you're trying to figure out the prime numbers that multiply together to give you that number.
Yeah, it feels like reverse engineering something, trying to find the original ingredients.
Exactly. And you're right. It is much harder. The simplest way to do it is trial division, where you just keep dividing the number by every smaller number until you find a factor. But here's the problem. The number of divisions you might have to do is roughly equal to the value of the number itself. And remember, we use efficient positional notations like binary or decimal. So the length of the input, the number of digits, is much smaller than the value of the number.
So a number that might take hundreds of digits to write down could be huge, but the input size for the algorithm is still relatively small.
Right. And so trial division, which might take a number of steps equal to that huge number, becomes completely impractical. Even for numbers with a manageable number of digits, it could take an eternity.
Okay, so the algorithm just gets overwhelmed.
Yeah, it basically explodes in complexity. And even though there are more sophisticated algorithms for factorization, none of them are truly efficient in the way that Euclid's algorithm is. They still take a ridiculously long time for large numbers.
And this isn't just a theoretical problem, right? The Stanford Encyclopedia talks about how important this is for cryptography, which obviously has huge real-world implications.
Absolutely. A lot of our online security, like for banking and communication, relies on the assumption that factoring large numbers is essentially impossible to do quickly.
Yeah.
If someone figured out a way to do it efficiently, it would be a big deal.
Yeah, it would break the internet, basically.
Pretty much. And, while we haven't definitively proven that factorization is intractable, there's a lot of evidence to suggest it is.
So we have relative primality, which is easy, and factorization, which seems impossible. And they're both based on prime numbers. It really highlights the core idea of computational complexity, this difference in how hard problems can be. Now, the Stanford Encyclopedia then goes on to talk about Church's thesis and the Cobham-Edmonds thesis. And I guess, how do these ideas, how do they fit into our understanding of the limits of computation, especially for a philosopher?
Yeah, so Church's thesis, that's a big one. It was developed back in the 1930s, and it's essentially saying that any function that can be computed, like by any conceivable mechanical process, can also be computed by a Turing machine.
Okay, a Turing machine. That's like the theoretical model of a computer, right?
Exactly. So Church's thesis gives us this really precise mathematical definition of what it means for something to be computable. But, and here's the catch, it doesn't say anything about how efficiently something could be computed.
So something could be computable in theory, but it might take a billion years to actually do it.
That's the idea. And that's where the Cobham-Edmonds thesis comes in. It tries to formalize this notion of feasible computability, what we can realistically compute with reasonable resources. It says that a function is feasibly computable if and only if it can be computed by a Turing machine in polynomial time.
Okay, so polynomial time again. That means the time it takes to solve the problem doesn't grow too crazily as the input size increases.
Right. And this is where the complexity class comes in. Text is
Mhm.
basically all the problems that can be solved in polynomial time. So the Cobham-Edmonds thesis is saying that text BFP represents the class of problems that are actually feasible to solve.
Okay, so text BFP is like the realm of practical computation.
Exactly. But the Stanford Encyclopedia points out that, the Cobham-Edmonds thesis isn't as universally accepted as Church's thesis.
Why is that? I mean, it seems pretty intuitive that there should be a distinction between what's theoretically computable and what's actually doable.
The main reason is the big unsolved question in computer science. Is text BFP actually equal to text BFNP?
Oh, right. Text BFP versus the $1 million question.
Exactly. So text BFNP stands for non-deterministic polynomial time. It's the class of problems where if you're given a solution, you can verify if it's correct in polynomial time.
So, like, if someone gives you the prime factors of a large number, you can easily multiply them together to check if they're right.
Exactly. A lot of problems that seem really hard, problems that we can only solve by brute force, are in text BFP. Now, if text BF were equal to text BFP, it would mean that for every problem where we can quickly check a solution, we could also quickly find a solution.
That would be huge, right? It would mean that a lot of problems we think are impossible are actually solvable.
Right, but we don't know if text BFP make FBFP, and because the Cobham-Edmonds thesis is based on text BFP being the class of feasible problems, this uncertainty about text BFP versus makes the thesis a bit shaky.
Okay, so it's like a foundational issue that throws a wrench into our understanding of what's truly feasible.
Precisely.
All right, so let's dive a little deeper into the technical stuff. The Stanford Encyclopedia mentions complexity classes like text BFN. For someone who's like trying to wrap their head around the formal side of this, what do these classifications mean?
Basically, they're ways of categorizing problems based on how much time and memory a Turing machine needs to solve them. So TextBFT is the set of all problems that can be solved in a certain number of steps, where the size of the input. And TextBF is similar, but it's about how much memory the machine needs.
So it's all about how the resources needed scale with the size of the problem.
Exactly. And then you have non-deterministic Turing machines, denoted as mathfrak, which are a bit more abstract.
Okay, non-deterministic. How is that different from a regular Turing machine?
Imagine a Turing machine that can make multiple guesses at the same time, and it only needs to find one correct path to get the answer. That's essentially a non-deterministic Turing machine. It's not actually a real machine. It's more like a theoretical concept.
So it's like it has the power of like infinite parallelism.
In a way, yeah. And this is how we define the class. A problem is in if a non-deterministic Turing machine can solve it in polynomial time. So it's like the machine can guess a solution and then quickly verify if it's correct.
And the interesting thing the encyclopedia points out is that non-determinism doesn't actually let us solve more problems. If a non-deterministic Turing machine can solve a problem, a regular Turing machine can too. It just might take a lot longer.
Right. It's about efficiency, not about what's theoretically possible.
Okay, so then we have this whole hierarchy of complexity classes like TextBFNL, TextBFMP, TextBFVIA, and so on. Can you give us a quick tour of what these classes represent, like a map of the computational landscape?
Sure. Think of it as a ladder, with each rung representing a different level of complexity. So you start with text BFL, which is problems that can be solved using very little memory, just a logarithmic amount. Then you have text BFNL, which is similar but with non-determinism. Then comes our polynomial time problems, and above that is text BFP, where you can verify solutions in polynomial time. And it keeps going up, with each class encompassing problems that require more and more resources.
Okay, so it's like each step up the ladder is a step up in difficulty, a step up in how much time and memory you need.
Exactly. And a big part of complexity theory is trying to figure out exactly where the boundaries between these classes are and whether some of these classes might actually be the same.
Okay, so like, is text BFP really different from text?
Right, and that brings us to the concept of reductions and text BFN completeness. This is how we identify the hardest problems within a given complexity class.
Okay, so like, how do we know which problems are the real heavy hitters?
The idea is that we can compare the difficulty of problems by seeing if we can use an algorithm for one problem to solve another. This is called reducibility. If we can efficiently transform problem A into problem B and then solve problem B, it means problem B is at least as hard as problem A.
So it's like if you can use a hammer to solve a problem, and you can also use that hammer to drive a nail, then driving a nail is at least as hard as solving that original problem.
That's a good analogy.
Yeah.
And then we have TeXBFNP hard problems. These are problems that are so hard that every problem in can be reduced to them. And if a hard problem is also in itself, that is called complete.
Okay, so complete problems are like the boss level, the ultimate challenge within.
Exactly. And the Stanford Encyclopedia mentions this problem called BHP, the bounded halting problem, as a classic example of an incomplete problem. It's basically about figuring out if a Turing machine will halt within a certain number of steps.
So it's like, can you predict whether a program will finish running or get stuck in an infinite loop?
Yeah, something like that. But the real breakthrough came with the work of Stephen Cook and Leonid Levin, who proved that a problem called the satisfiability problem is also complete.
And that's about logic, right? Trying to find a way to make a logical formula true.
Exactly. And this connection between a logic problem and computational complexity was huge. It showed that you could translate any problem into an instance of. So if you could solve efficiently, you could solve every problem inefficiently.
Okay, so it became like the Rosetta Stone of complexity theory.
That's a good way to put it. And once they proved that was complete, it led to a domino effect. Researchers started proving that tons of other problems in all sorts of fields were also complete, just by showing that they could be reduced to meant. The encyclopedia mentions problems like the traveling salesperson problem and programming.
And this whole web of reductions shows how interconnected these seemingly unrelated problems are. It means that if we could crack one of them, if we could find a fast algorithm for an complete problem, we'd basically unlock the whole class.
Exactly. It would mean text BFP, and that would change everything.
But of course, no one's been able to do that yet.
Right. And the fact that we've been trying for so long and failing is pretty strong evidence that these problems really are inherently difficult.
Okay, so we've talked about text BFP, but the landscape of computational complexity goes even further. The Stanford Encyclopedia mentions in the polynomial hierarchy. For someone who's, interested in the limit of logical reasoning and the nature of proof, what are these all about?
Yeah, so text BFAPP is kind of like the opposite of text BFP. It's the class of problems where you can efficiently verify a no answer.
Okay, so instead of proving something is true, you're proving something is false.
Exactly. For example, think about the problem of determining if a logical statement is a tautology, meaning it's always true. That problem is in text BFCONP, because if someone gives you a counterexample, a way to make the statement false, you can easily check if they're right.
So if text BFP, does that mean text BFPMP too?
That's right, because if text BFNP, then solving a problem and solving its opposite would be equally easy.
Okay, but there are people who think that text BFP and P are actually different, right?
Yeah, most complexity theorists believe that.
Text BF and P. So it might be the case that some things are easy to prove true, but really hard to prove false.
Exactly. And then there's this interesting class of problems that are in both text BFN and text BFP, denoted as text BFP, CAX BFEMP.
What's so special about those problems?
Those are problems where you can efficiently verify both yes and no answers. And Stanford Encyclopedia brings up a familiar example.
Right, because if someone gives you the factors, you can easily multiply them to check, and if they tell you a number is prime, you can, I guess there are tests for that too.
Exactly. There are efficient primality tests. So the NC factorization is a good example of a problem that's in TextBFNP, but that we don't know for sure is in TextBF.
So it's like there might be this middle ground, problems that are harder than TextBF, but not as hard as the really tough problems in TextBF.
Exactly. And then going even further, we have the polynomial hierarchy, denoted as TextBFNP.
Okay, the polynomial hierarchy, that sounds intimidating.
It's basically a way to classify even harder problems, problems that might be beyond text BFEs. It's based on this idea of alternating quantifiers, like for all and there exists, where the computations within those quantifiers are limited to polynomial time.
So it's like you're layering complexity on top of complexity.
Exactly. And the big question about the polynomial hierarchy is whether it goes on forever or if it eventually collapses at some point, meaning all the higher levels are actually equivalent.
Okay, so it's like, is there an ultimate level of complexity or does it just keep going?
Right. It's another one of those big open questions in complexity theory. And the fact that we have all these unsolved problems, it really shows how much we still don't understand about the nature of computation.
Okay, so we've covered a lot of ground here, from text BFP and the polynomial hierarchy, but let's bring it back to philosophy. The Stanford Encyclopedia starts by asking, what's the philosophical significance of BFNP?
I mean, if it turns out that these classes really are different, what does that tell us about, like, the nature of problems and the limits of knowledge?
It would be a huge deal philosophically. I mean, it would formally confirm this intuition we have that some problems are just inherently harder to solve than to verify.
Right, like, it's much easier to check if a puzzle is solved correctly than to actually solve it yourself. Exactly.
Yeah.
And if text BFP, it would support the Cobham-Edmonds thesis, the idea that really does represent the class of feasible problems.
So it would be a win for the practical side of computation.
Yeah, in a way.
Hmm.
But it also raises some interesting questions about creativity and the nature of mathematical discovery. The encyclopedia mentions this letter that Kurt Gödel wrote to John von Neumann back in 1956.
Kurt Gödel, the logician. Right. What did he have to say about all this?
He was thinking about the difficulty of finding proofs for mathematical theorems. He asked whether finding a proof of a certain length would always require, like, a brute force search through all possible proofs of that length.
So it's like, is there a shortcut to finding proofs, or do you always have to trudge through the mud?
Right, and verifying a proof is generally considered a problem in text BFP. You can do it relatively quickly. But finding a proof, that seems like it could be a problem in text.
Because if someone hands you a proof, you can check if it's right.
Exactly. So if text of BFMP, it would mean that finding proofs is essentially no harder than checking them.
Which would be pretty mind-blowing, right? It would mean that mathematical discovery could be automated, at least in principle.
Yeah, it would suggest that there's no real magic to mathematical insight, that it's all just a matter of efficient computation.
But if text BFNP, it would mean that finding proofs really is a fundamentally different and potentially harder task than just checking them.
Exactly. It would suggest that there's something special, something inherently creative about mathematical discovery.
Okay, so it has big implications for how we view mathematics and the role of human intuition.
Absolutely. And the encyclopedia also points out that the statement, text BFNP, can actually be expressed within the framework of first-order arithmetic, which is a foundational system in logic.
So it's like the question itself is a mathematical object.
Exactly. And what's interesting is that this formulation suggests that the text BFP versus text BFP problem might be independent of our current axiomatic systems, like Pinot arithmetic or ZFC.
Meaning we might need entirely new mathematical tools to even figure out if it's true or false.
Right. It's a question that could push the boundaries of mathematics itself.
Okay, so we've talked about the big picture implications of text BFP versus text BFNP. Now let's zoom in a bit. The Stanford Encyclopedia discusses the computational complexity of basic logical tasks, like checking if a formula is satisfiable or valid for a bunch of different logics. And it turns out that a lot of these tasks are really hard, often complete, or even worse.
Right. It's not just about whether a problem is solvable in principle, but how much computational effort it takes to actually solve it. And for many logics, even seemingly simple tasks, like determining if a formula is always true, can require a huge amount of computation.
So it's like the logic itself is computationally complex.
Exactly. And the Stanford Encyclopedia includes this table that summarizes the complexity of these tasks for all sorts of logics, like classical logic, intuitionistic logic, modal logic, you name it. And it's pretty clear that for many of these logics, doing basic reasoning can be incredibly difficult.
And philosophically, what does that mean? I mean, we tend to think of logic as this pure and absolute system of reasoning.
Right. But computational complexity throws a wrench into that. It suggests that even if logical truths are absolute, our ability to access them, to actually figure them out, is limited by computational constraints.
So our brains and even our computers might not be powerful enough to handle the full complexity of logic.
Exactly. And this directly challenges this traditional idea in philosophy that logical knowledge is a priori, meaning we can know it without any experience. If it's computationally infeasible to determine logical truths, then how can we claim to know them innately?
Right. It's like if it takes a supercomputer a million years to figure out if something is logically valid, how can we say that we just know it?
Exactly. And this connects to this problem in epistemic logic, the logic of knowledge, called logical omniscience.
Logical omniscience, what's that?
It's this idea that a rational agent should know all the logical consequences of their beliefs. So if you believe A, and A implies B, then you should also believe B. But computational complexity shows us that this is an unrealistic expectation.
Because there might be consequences of our beliefs that are just too complex for us to compute, even if they are logically valid.
Exactly. And the Stanford Encyclopedia goes on to talk about proof complexity, which is a field that studies the length of proofs in different formal systems. And there's this theorem, the Cook-Rechow theorem, that links the existence of short proofs to the question of whether text BFNP.
Okay, so the length of proofs matters, but how does that tie into text BF, EFN,
Oh, the theorem says that if there exists a proof system where all valid statements have short polynomial length proofs, then text BFMP.
So, if we could always find short proofs, it would mean that proving something true is no harder than proving something false.
Exactly. But since most people think text BFNK, it means that for many logics, there are going to be valid statements that require really long, complicated proofs.
And this is where Haken's result about the pigeonhole principle comes in, right? This seemingly simple logical statement that requires exponentially long proofs in some systems.
Exactly. It shows that even for simple truths, the proofs can be incredibly complex. And if you think about it, if a proof is exponentially long, it's basically useless to us.
Because we'll never have the time or resources to actually read and understand it.
Exactly. So proof complexity gives us another way to measure the difficulty of logical reasoning. It's not just about finding a proof, but finding one that we can actually comprehend.
So it's like, even if a truth is logically provable, it might be practically unknowable.
Exactly. And this has big implications for our philosophical understanding of knowledge.
Yeah.
It means that the set of things we can actually know might be much smaller than the set of things that are logically true.
Okay, so computational complexity is forcing us to rethink our ideas about knowledge and proof.
Absolutely.
All right, let's move on to the next topic. The Stanford Encyclopedia talks about descriptive complexity, which is this idea of using logic to characterize complexity classes. Can you explain what that's all about?
Yeah, it's basically about trying to find a logic that captures the essence of a particular complexity class. So, for example, Fagin's theorem shows that the class can be characterized by a type of logic called existential second-order logic.
Okay, so there's a connection between a complexity class and a logical language.
Exactly. And then the Immermann-Vardy theorem shows that the class, at least for ordered structures, can be captured by first-order logic with the least fixed point operator.
So it's like you're using logic to define what it means to be in a particular complexity class.
Exactly. And this gives us a whole new way to think about computational complexity in purely logical terms.
And the fact that we haven't found a logic to capture for unordered structures shows that there are still some mysteries to uncover.
Absolutely.
Okay, we're getting close to the end here. The Stanford Encyclopedia also briefly mentions bounded arithmetic and strict finitism. Can you quickly summarize how those connect to computational complexity?
Bounded arithmetic is basically a way to study complexity within the framework of arithmetic. So you have these theories of arithmetic that are limited in certain ways, and the functions that are provable in those theories correspond to certain complexity classes. It's a way to connect computational power to proof theoretic strength.
Okay, so it's like a bridge between logic and complexity.
Exactly. And then strict finitism is this philosophical view that we should only consider numbers and objects that are feasibly constructible. It's very much in line with the concerns of computational complexity.
Right, it's about what we can actually work with in practice.
Exactly. But the encyclopedia points out that strict finitism runs into some problems, particularly with this idea that there's some upper bound on the size of feasible numbers.